So good afternoon, everyone. Welcome to the afternoon session of day 4. Today to chair the session, we have Dr. Praveen Garg. He is an assistant professor in Department of Mathematics, University of Rajasthan. He did his BSc and MSc from University of Rajasthan and then went on to do PhD from Banasthali University. He has more than 15 years of teaching experience. He has also undertaken a project under UGC. He is presently supervising 1 PhD student and 2 MPhil students. He has published more than 20 papers. Other than that, he has attended many faculty development programs, workshops, and conferences. He has also organized more than 15 workshops, conferences, and training programs. He is a lifetime member of International Academy of Physical Sciences, ADMA, and Rajasthan Ganit Parishad. So we are happy to have you. Please take over.
Thank you, ma'am. So good afternoon, everybody. So now at the outset, I thank to Dr. Rajesh Singh and Dr. Deepakshi to give me this great opportunity to introduce dynamic, vibrant, and renowned mathematician as well as graph theorist, Dr. Purnima Gupta Madam. Am I audible?
Yes, sir. You are.
Okay. After obtaining her BA honors in mathematics and MA mathematics degree with first rank from University of Delhi, she pursued her Master of Science at University of Toronto and later completed her PhD in mathematics, specializing in graph theory from University of Delhi under the guidance of very much respected and great mathematician Dr. B.D. Acharya sir. Dr. Purnima Gupta ma'am has done pioneer work in the field of graphoidal covers. She has more than 35 research publications in journals of national and international repute with high impact factor. And she has delivered more than 20 invited talks in national and international level conferences and workshops. She has guided 2 students for PhD and 1 for MPhil degree from University of Delhi. Dr. Gupta held a responsible position as Director, Central Board, State Bank of India. She has served University of Delhi for around 40 years. She is adjunct professor and professor of eminence at Ramanujan College, University of Delhi. She is an executive member of Ramanujan Mathematical Society and life member of several academic bodies in India and abroad. With these remarks, I invite Dr. Purnima Gupta Madam to deliver a talk on domination in graphoidally covered graphs. Over to Dr. Purnima Gupta ma'am.
Thank you, Dr. Praveen Garg, for such a kind and nice, making me feel great. You have made me feel 10 years
It's
younger.
my privilege.
You have made me feel 10 years younger.
Thank you, ma'am.
And thanks, Professor Sampath Kumar, for joining. It's an honor for me, sir. So, and before I start with the main theme of my talk, I want to congratulate Dr. Rajesh Singh and team for organizing this pre-conference workshop of ADMA under the flagship of Ramanujan College, University of Delhi. I have special admiration for the principal of this college, Dr. S.P. Agarwal, who is always forthcoming to any such idea and for his encouragement to the young faculty of this relatively young college. This pre-conference workshop being held at this trying time of Corona is actually a service to the nation, as it has brought hundreds of researchers from all over the country on a common platform and has diverted the minds of all the participants from the fear of COVID-19 and made them indulge in something positive and fruitful. My appreciations again for Dr. Rajesh Singh and Dr. Dipakshi Sharma for this endeavor of theirs. I also thank them for giving me this opportunity to connect you all. Thank you, and I start with my screen sharing. So now, can I start, Dr. Rajesh?
Ma'am, your talk is not visible to us.
The slide is not visible?
Yes, ma'am. Ma'am, you need to click the green button, green share screen button, and after that you will see you will have to select that file RTGL graphite domination PDF, and then click on the share on the right side. Shall I share your screen, ma'am?
Just wait.
Okay.
Rajesh, can you see now?
No, not yet, ma'am.
What to do then?
She has to open the file, no?
First,
She has to open I think she's not opening the file.
ma'am, is that PDF open in your laptop? Shall I share from my end, ma'am? I can also share. So
Then can I not move the
then you
slide?
will have to guide me to change
Oh.
the slides.
Purnima, after clicking the share screen, you go to PDF and then open that PDF. Now it
Okay,
yes,
okay. Now it is there.
she was not opening the PDF. Now it
Yeah,
Now
now
it's
it is
fine?
there, ma'am. Yes, ma'am. Now it is fine.
make a full screen,
Yes, it is full screen, ma'am.
but it's
Okay.
only small only.
Yeah, because they are made differently from the actual presentation point of view.
Okay.
So as you are, just wait, what is happening?
It's fine, ma'am.
मुझे ऊपर का, so the title of my talk is Domination in Graphoidally Covered Graphs. And as you are seeing, the title involves two words, domination and graphoidally covered graphs. So both the concepts, graphoidally covered graphs and then domination in graphoidally covered graphs, they are based on the concept of graphoidal cover of a graph. Graphoidal covers and graphoidally covered graphs provide a totally new horizon to work on and offer tremendous scope for research. So the concept of graphoidal cover was introduced in the year 1987 by Dr. B.D. Acharya and Dr. E. Sampath Kumar for finite graphs. The concept was later taken up by Dr. Armugam and his group, and number of theses were written on graphidal covers and graphidal covering number of a graph. After a while, Dr. Acharya and myself took this up. So since earlier it was defined, the graphidal covers were defined only for finite graphs, we extended the concept of graphidal covers to infinite graphs. And not only that, we extended the concept of domination to discrete structures called graphidally covered graphs. So this is a totally a new concept of domination, and it was introduced by Dr. B.D. Acharya and myself as a student. And this provides ample scope for research, and for the newcomers, it's a very, very fertile area. So now let me look at, and on this topic, a 30-page research paper based on domination in graphidally covered graphs was published in the journal Discrete Mathematics in the year 1999, and the topic was domination in graphidally covered of a graph. It was a 30-page paper, and it covers lots of topics. So those interested must go through this paper, and it will give lot of problems for research. So now, what are graphidal covers of a graph? What is graphidal cover of a graph? A graphidal cover of a graph, not necessarily finite. Please note one thing. We are defining graphidal cover for a graph. The graph can be infinite or finite. So it's a collection psi of non-trivial paths, not necessarily open, not necessarily finite. So another.
बोलो कैसे हो?
Yes, Dr. Mukti.
हाँ मैं ठीक हूँ.
You want to say something?
No, ma'am. She was on some call, so you can proceed, ma'am.
Okay. So I was starting with the definition of graphidal cover of a graph. So it's a collection psi of non-trivial paths. The paths are not necessarily open and not necessarily finite. What does it mean? This means the paths can be infinite. The paths could be closed, means cycle, such that no two paths have a common internal vertex, and every edge of G is in exactly one path inside. So if we look at the definition, we see that a graphidal cover of a graph is a decomposition of the edge set of the graph into internally vertex disjoint paths. So since if I take the full edge set, the paths of length 1, then this obviously satisfies the condition. So the edge set itself is a graphidal cover of the graph, and this is called the trivial graphidal cover of G. So like in this K4 minus X in this graph, the edge set E1, E2, E3, E4, A5 is itself a graphidal cover of the graph G. So another example, please look at this graph. The edge set has been decomposed into 4 paths. What are the paths? P1, P2, P3, and P4. Please notice that P4 is a cycle. W, W1, W2, W3, W. P1 is W, U1, U2. And P3 is a path of single length. That's also possible. And P4 is and P2 and P3 is V1Z, and P1 is WU1, U2. So we see that if we decompose the asset into 4 such paths, so they satisfy the condition of the graphoidal cover of a graph, because no two of them have a common internal vertex, and P4 is a closed path. With W, because in my, when I have written P4, I am starting with W and ending with W. So that means W is the end vertex of this path. And for the path P1, there are 2 end vertices, namely W and U2. So it can also be easily seen that any ER decomposition of a finite 2 connected or 2S connected graph G is a graphoidal cover of G. Please have a look at this. So this is a 2 connected graph. So I look at an ER decomposition of this graph with C as the initial cycle and the years being E1, E2 and E3. We observe that C, E1, E2 and E3 satisfies the conditions of a graphoidal cover and is therefore a graphoidal cover of G. Thus, the graphoidal covers of a graph can also be looked upon as generalization of the notion of an ER decomposition of a graph. Another example of a graphoidal cover can be seen if we take a mobile aerial view of mobile traffic at any junction. Only one stream can be moving, and rest all the streams have to stop there. So that means that junction can be an internal vertex to at the most one moving stream. So this road network at a particular instant is also an example of a graphoidal cover of a graph. Given a graph G and a graphoidal cover psi of G, the ordered pair G psi is called a graphoidally covered graph. So please notice one thing. If psi is the trivial graphoidal cover, or meaning thereby if psi is E itself, then this is our original graph only. So meaning thereby every graph can be considered as a graphoidally covered graph, but not vice versa. A path P in a graphoidal cover psi of G is called a psi edge of G. Like in a graph, we are having edges. So here I am having psi edges. So now I have already defined discrete structures which we call as graphoidally covered graphs. And now I am calling the edges corresponding to psi, because given a graph G, there could be many psis. If a graph is an infinite graph, there could be infinite number of psis. But if a graph is a finite graph, obviously there will be finite number of graphoidal covers. And correspondingly, there will be different psi edges. So in general, in a graphoidal cover, as we said, as I started with, that the paths need not necessarily be finite and open. So in general, there are 4 types of paths in a graphoidal cover of a graph. What are the 4 types? Finite open path with 2 end vertices, a closed path with the same vertex as the starting and the end vertex, that's the coincident end vertex, and it is specified by the graphoidal cover which we are talking. Because in another graphoidal cover, the cycle may be there, but the end vertex could change. There could be one-way infinite paths, which we call as ray, and a one-way infinite path has exactly one end vertex, and there could be two-way infinite paths. They could also be they could also belong to the graphoidal cover or the collection. So that could be a path in the graphoidal cover, because graphoidal cover is nothing but a collection of paths. And as we said, originally in a graph, we are having only one kind of edge. But here I said there could be 4 types of edges. finite open, closed, one-way infinite, two-way infinite, 4 types. And similarly, there we are having vertices, only one type, vertex. But now I am having 3 types of vertices. What are the 3 types of vertices? A vertex, which is, the vertex, first vertex is psi exterior vertex. A vertex which is only an end vertex. It is not an internal vertex of any path of psi. There are psi interior vertex. Psi interior vertex means this works only as an interior vertex. This is not an end vertex to any psi edge, to any path belonging to psi. And the third vertices are the composite vertices, which play a role of a internal vertex and the end vertex also. Like I showed you the example of a traffic and at any junction. So only one stream is moving. So for that it has become an internal vertex. And for others which are hurting, it has become the end vertex. So in this figure, W is a composite vertex. It is an internal vertex for P1 and end vertex for P2 and P3, these 2 paths. One thing I forgot to tell you people, that in the diagrammatic representation of any graphoidal cover, the end vertex, this exterior vertex, is represented as a filled black circle, like in this W. And internal vertex is a unfilled circle. And the composite vertex, because it is internal vertex to P1, so for that it is unfilled circle. And for others, there are tangents. We put tangents. Like if it is end vertex to P2, I put a tangent there. So it is end vertex to as many paths, as many tangents are there. So now there are diagrammatic representation of 2 different graphoidal covers of K4. Please look at the complete graph K4. And if you look at the graphoidal cover psi1, it has just 2 paths. What are the paths? What are the paths? Please have a look. D, A, B, C. D, A, B, C. And the other one is A, C, D, B. So meaning thereby every vertex in this graphoidal cover is an internal vertex as well as end vertex. Both, it's playing both the roles. You look at all the 4 vertices, there is an unfilled circle and there is a tangent. For the same graph K4, please look at another graphoidal cover. We call it psi2. Psi2 has 3 paths. What are the paths? One is BD, just a single edge of length 1, because that's also a path. Another is DAC, DACD. So that's a cycle with D as the end vertex. And the third is ABC. Just sorry for 1 minute, please. This is example of an infinite tree. Previously, I was looking at the finite graphs. Now this is an infinite graph. It's an infinite tree. And as you see, each of the psi is a one-way infinite path. Starting from W, and then everywhere, every vertex except W. W is a psi exterior vertex. And all other vertices are composite vertices. They are playing both the roles. They are internal as well as end vertex. Because everywhere you find one tangent. So here is a graph, which is an infinite graph, and it has all kinds of paths. All kinds of paths means P1, if you look at P1, it's a two-way infinite path. It belongs to psi. If you look at P2, it's an open finite path. And if you look at P3, it's a one-way infinite path with W as an end vertex. And P4 is a closed path with W as the coincident end vertex. You will observe that all the conditions are satisfied. No two paths have a common internal vertex. So this is an example of an infinite graph having all kinds of psi edges. So now comes the real thing. Now we define, I have already defined a discrete structure which is called a graphoidally covered graph. Now I come to adjacency. How do I define adjacency? Because normal adjacency in a graph, everyone knows that UV are adjacent if UV belongs to E, EG. Now, two vertices U and V in G are said to be psi adjacent if there exists a path P in psi with U and V as its end vertices. In this case, we say that U is psi adjacent to V and we write U psi V. That means whenever there is a open finite path, U open finite path with U and V as its end vertices, and if it belongs to psi, then I say U is psi adjacent to V. And if it is a cycle starting from U and ending at U, then I say that U is psi adjacent to U itself. So here is an example. Please look at this graph, and the graphoidal cover is evident from the way it has been drawn. So there are four paths, P1, P2, P3, P4. The path P1 is A, B, C. So that means A and C, A and E, sorry, A and E, A, B, E. So A, B, is it C or E? A, B, E. A, so that means A is psi adjacent to E, and on this side A, D, G. That means A is also psi adjacent to G, and CD is also belonging. So C and D are psi adjacent to each other. And now I also having A, C, F. So that means A and F are psi adjacent to each other. Please notice one thing. Like A and C are adjacent in our own original graph, or like A and B are adjacent, but here they are not psi adjacent. A and B are not psi adjacent. A and C are not psi adjacent. A and D are not psi adjacent. Similarly, B, E are not psi adjacent. So this is the difference. So another, for the same graph, as I said, we can have number of graphoidal covers. So please look at another graphoidal cover. This graphoidal cover consists of four paths. One is a closed path, A, C, D, A. Another is A, B, E. Then P4 is CF, just path of length 1. P3 is the original path of length 1. So here you say A is psi adjacent to itself. A is also psi adjacent to E. Then C is psi adjacent to F. D is psi adjacent to D. So here comes the concept of domination in graphoidally covered graphs, and which becomes the original domination when psi becomes the trivial graphoidal cover, that is psi is the edge itself. A set D contained in V is a psi dominating set or psi dom set of the graphoidally covered graph G psi if for every vertex V in V minus T there exists if for every vertex V in V minus D, there exists a vertex U in D such that V is psi adjacent to U. Am I audible, please? Dr. Praveen, Dr. Rajesh, can you please tell me?
Yes, ma'am, you are audible.
Yes, sir, yes, sir.
I have to speak, I think, slowly because my throat is not cooperating.
It's fine, ma'am, it's fine.
Oh,
A set D contained in V is a psi dominating set of G psi. If for every vertex V in V minus D, there exists a vertex U in D such that V is psi adjacent to U. Please notice one thing. In our dominating set, what we are saying, D is a dominating set. If for every vertex V in V minus D, there exists a vertex U in D such that V is adjacent to D. V is adjacent to U. But here I'm saying if V is psi adjacent to U, that is the difference. And that's why it gives such a much bigger platform to work on, because we are able to extend. So if psi is EG, a psi dom set of G is the usual dominating set, as I just now explained, because then every psi as is of single length. So whatever are adjacent in the graph, they are adjacent in G psi also. Further, there is a remark which says a psi dom set of G and a dominating set of G are totally different entities. So a psi dom set of G need not be. So another example, please have a look. After having given the definition, I would like to show it to you because the example which we considered, and in this example, I can see that A, B, and C is a psi dominating set of the graphoidally covered graph G psi. Why it is a psi dominating set? Because then after A, B, C, what is V minus D consists of? E, F, G, and D. So E is adjacent to A, psi adjacent to A, F is psi adjacent to A, G is psi adjacent to A, all of them are psi adjacent, and D is psi adjacent to C. So this is a psi dominating set. But please notice one thing, ABC is a psi dominating set, but it is not a dominating set. So that's the difference. So in general, a psi dominating set need not be a dominating set of G and vice versa. Like in this example with this graphoidal cover, A, C, E, B, D, F, C, B, and D, A. This is the graphoidal cover. So we see that AB is a psi dominating set. Why it is a psi dominating set? Because E is psi adjacent to A, F is psi adjacent to B, D is psi adjacent to A, and C is psi adjacent to B. But AB is a psi dominating set, but AB is not a dominating set. While CD is a dominating set. The vertices CD, you can observe, it's a dominating set, but it is not a psi dominating set. So they are totally different entities. So as I've already talked about psi dominating sets. So the set of all psi dominating sets of the graphoidally covered graph G psi, I will denote as D psi G. In case of psi is equal to E, it will become our usual set of dominating sets. Like in our dominating set, the full set is always a dominating set. Always it happens. So similarly, the full set is always a psi dominating set of the graphoidally covered graph G psi for any graphoidal cover psi of G. Or I can say VG belongs to D psi G for any graph G and for any graphoidal cover psi of G. Now question arises. In general, do there exist graphs for which there exists a graphoidal cover psi such that VG is the only psi dominating set for the graphoidally covered graph G psi? Please try to understand the question. Question is, do there actually exist graphs for which there exists a graphoidal cover psi such that VG is the only psi dominating set for the graphoidally covered graph G psi? If psi is our trivial graphoidal cover, that is if psi is equal to E. So in graphs, if I say which are the graphs for which only full set is the dominating set, what will happen? Which are those? Those are the graphs which are totally disconnected, consisting of isolates. But here in graphoidally covered graph, the situation is there are several infinite type of structures, and which I will be showing that which can admit such a graphoidal cover such that VG is the only psi dominating set. But again, there will be infinite number of graphoidal graphs for which there may not exist such a graphoidal cover. So my question was, do there exist graphs for which there exists a graphoidal cover such that VG is the only psi dom set for the graphoidally covered graph G psi? My answer is yes. Please have a look at this finite graph. This finite graph is, so for this finite graph, I can have a graphoidal cover such that for that graphoidal cover psi, VG is the only psi dominating set. What is my graphoidal cover? Consists of two cycles, C1 and C2. C1 starts from U2, ends at U2. And C2 starts at U5 and ends at U5. So this is a graphoidal cover because end vertex of C2 is internal vertex of C1 and end vertex of C1 is internal vertex of C2. So this happens to be a graphoidal cover, and for this graphoidal cover of this graph, VG is the only psi dominating set of G psi. So this has shown the existence. Again, I also have an example of an infinite graph which possesses a graphoidal cover such that VG is the only psi dominating set of G psi. Please look at this consists of 6 paths. Out of the 6 paths, 3 are cycles and 3 of them are one-way infinite paths. And I am able to so draw the graphoidal cover such that VG is the only psi dominating set of G psi. I am able to do it because in this graphoidal cover, there is no finite open path belonging to psi. But the question arises, is it always possible to find such a graphoidal cover? Because I have shown that there are graphs which are finite as well as infinite for which there exists a graphoidal cover such that this VG is the only psi dominating set. That is D psi j consists of a singleton VG, the set full set itself. So now question arises, does every graph have a graphoidal cover psi such that VG is the only psi dom set of G psi? It's a very natural question because it looks as though we can always draw. No, it's not always possible. There comes the study. So here, this is a finite graph. Come what may, whatever way, it's an exercise for the students, for the researchers. You cannot draw a graphoidal cover psi such that VG is the only psi dominating set of G psi. So please notice all those people who want to try, they can take a screenshot of this slide. And again, how about infinite? It looks maybe in infinite it may be possible. No, even in infinite, look at this graph. Come what may, whatever way you may try, you cannot find a graphoidal cover such that VG is the only psi dominating set. Meaning thereby, you will have to have a finite open path belonging to any graphoidal cover of this graph. And then if there is a finite open path, then that gives an adjacency and you get a non-trivial psi dominating set. So thus given a graph G, there may or may not exist a graphoidal cover psi such that VG is the only psi-dom set of G. So that means there is an importance. There may or may not exist, but the graphs finite or infinite for which there exists a graphoidal cover psi of G such that VG is the only psi dominating set of G, then we call graph G to be graphoidally independent. This is a very important concept based on domination, because this everything is coming from domination. So this is an important definition. A graph G is said to be graphoidally independent if there exists a graphoidal cover psi of G such that VG is the only psi dominating set of G. Now question arises, what can we say about the structure of graphoidally independent graphs? Which graphs could possibly be graphoidally independent? Which are the graphs for which we can have a graphoidal cover psi such that VG is the only psi dominating set? So actually the problem is fully settled for finite graphs, and it is a published paper, and this says that if G is a connected finite graph, then there exists a graphoidal cover psi such that d psi G is equal to VG if and only if G is 2s connected and one of the following holds. What are the one of the? G is a cycle cactus. It's a cactus, each of whose blocks is a cycle. Or first of all, I have already said it's 2s connected. G has exactly one non-trivial, non-cycle block, which is a necklace block. What is a necklace block? It's a sequence of cycles, and every adjoining cycles starting and beginning from the cycle, and this looks like a necklace. I will show later the picture of this, and every other block is a cycle. It's published in AKCE in the year 2007. So this is a possible structure. As I said, this is a necklace block. There's a possible structure. There could be many, but something like this. What can we say about the structure of graphoidally independent infinite graphs, which is the theme of this talk? What can we say about the structure of graphoidally independent infinite graphs? So as regards the structure, we have two necessary conditions for an infinite graph to be graphoidally independent. So whenever we have to check, so we can check from these two necessary conditions, which have to happen, which have to be true if a graph is graphoidally independent. What are the necessary conditions? Necessary conditions are G has at most one pendant vertex. Another is G has no free path of finite length. What is a free path? Free path. So thus, from these conditions, I can say, I will explain free path after a while, that if a graph has more than one pendant, obviously answer is no. If a graph has a free path of finite length, I'll say no, it cannot be graphoidally independent. So an infinite graph having more than one pendant vertex or a free path of finite length cannot be graphoidally independent. What are free path? Free path is a maximal path, each of whose edges is a bridge. So please have a look an example. Here, if I look at Q, it's a finite free path. It's finite and each of the edges is a bridge. But if I look at P, it's an infinite free path. And if I look at the graph G2, the R is a infinite, it has only one free path, and which is infinite. While G1 has two free paths. One is finite and one is infinite. Q is finite free path, P is infinite free path. So now question arises, are the two conditions sufficient as well for an infinite graph G to be graphically independent. The conditions are necessary, but are they sufficient? The answer is a strict no, because we have a graph which satisfies both the conditions. It has no pendant vertex, no free path of finite length, but I give it as an exercise. This graph cannot have a graphidal cover psi such that VG is the only psi dominating set of this graph. So this graph is, although satisfies the conditions, but is not graphidally independent. So what does it mean? That means the conditions are not sufficient in general. But although the conditions are not sufficient for an arbitrary infinite graph to be graphically independent, but in our study, we have proved that they are sufficient for infinite trees and for infinite unicyclic graphs. In fact, for trees, the two conditions are equivalent. So now this is graphically independent infinite trees. An infinite tree G is graphically independent if and only if G has at most one vertex of degree 1. Either it has no vertex of degree 1 or it has at most one vertex of degree 1. So then it is graphically independent. So conditions are sufficient. So here is an example. This is graphically independent and it has no vertex of degree 1. And another example is this infinite tree having a vertex of degree 1, and this is graphically independent because each of the psi's is a one-way infinite path, as I explained previously also. So now I come to graphically independent unicyclic infinite graphs. A unicyclic infinite graph is graphically independent if and only if, as I said, the necessary conditions are sufficient for unicyclic infinite graphs. So it is graphically independent if and only if G has at most one vertex of degree 1 and G does not have a free path of finite length. So here is one example of an infinite unicyclic graph which is graphically independent. It has one vertex of degree 1 and no free path of finite length. So please notice that the cycle belongs to psi, and for this vertex U is the end vertex of the cycle and the internal vertex of the one-way infinite path starting from V. After having proved that the two necessary conditions are sufficient as well for infinite trees and infinite unicyclic graphs to be graphically independent, a natural question arises: what about graphically independent infinite cactus? Are they graphically and are the conditions sufficient for infinite cactus? They have been proved to be sufficient for trees, infinite trees, and for infinite unicyclic graphs. What about infinite cactus? So are these conditions are the infinite cactus satisfying the following two necessary conditions graphically independent? This is the question. So there was a conjecture by my mentor, my guru, Dr. V.D. Acharya. He conjectured that every infinite cactus, because we were not able to find any example, neither the proof was coming, nor the example was coming. Every infinite cactus satisfying the two necessary conditions is graphically independent. So this was the conjecture by sir. So this conjecture was, it remained a conjecture and remained open for a very long time. But very recently there was a breakthrough, and I gave this problem to my student, Dr. Dipti Jain, and she disproved the conjecture by providing an example of an infinite cactus which satisfies both the conditions yet does not possess a graphidal cover psi such that Vg is the only psi dominating set of this infinite cactus. So it was a breakthrough, because once we know that the conjecture is not true, then we start working on it. What additional is required? So all this is the work of Dr. Deepti Jain, and I'm very happy with her work on this subject. And this was the example which she brought to me, and she said, ma'am, look at this. What is happening? So this is an infinite cactus, satisfies both the conditions because it has only one pendant vertex and it has no free path of finite length. But you may try, however you may try, you cannot find a graphidal cover psi such that Vg is the only psi dominating set. So this problem is quite a challenging problem, and this is still an open problem. Characterize infinite cactus G which possesses a graphidal cover psi such that Vg is the only psi dominating set of G psi. So now let me change from the pendant vertices and the free paths. All through I'm talking of an infinite graph having a pendant vertex or a free path of finite or infinite, finite length or infinite length. What happens if there is a graph which has neither a pendant vertex nor a free path, no free path, finite or infinite? What happens to, should they be graphidally independent as it looks like? Because our talk is, should such infinite graphs be always graphidally independent? And the answer is no. This infinite graph has no pendant vertex, no free path, yet you cannot find a graphidal cover. You cannot find a graphidal cover such that Vg is the only dominating set corresponding to that graphidal cover. So this gives us a problem to work on. That what can we say? How to characterize which graphs could be graphidally independent? So graphs which neither have a pendant vertex nor a free path irrespective of finite, they are two edge connected graphs, and we have fully characterized infinite two edge connected graphs which are graphidally independent. So here is a theorem. A two edge connected infinite graph G is graphidally independent if and only if exactly one of the following holds. Every block of G is a cycle, that is G is a cycle cactus, and either this or G has exactly one non-trivial non-cycle block which is a necklace block, which I have already explained to you, and every other block is a cycle. This is a necklace block which I have already, so there there is no repetition, it's a sequence of cycles starting and ending with the same cycle. So this is an example, this is a necklace block, and this is an infinite two edge connected graph, and only this kind of graphs could possibly be graphidally independent. But the general problem is still open, and the problem is characterize graphidally independent infinite graphs. The problem is interesting because of infinite graphs. Because in infinite graphs, you have infinite number of possibilities. So this is an open and a challenging problem. So these are my references. I end with that open problem and make it open for the participants to work on. And these are the two references. And lastly, this talk of mine is dedicated to my teacher, the most revered Dr. B.D. Acharya. And this was an epilogue by him, which is so true always. This is the logic may throw open paths to visualize infinity, but seeing infinity, however, seems possible only through exploring our consciousness. This was, so my all respects. I hope my sir is listening to this talk, and he must be actually giving his responses also. Thank you, everyone. Thank you, Dr. Rajesh. Thank you, Dr. Praveen.
Thank you, ma'am.
Thank you. Yes, thank you, Dr. Purnima Gupta, for this wonderful talk. And really, it is an eye-opener talk. And I'm very sure all the participants who are joining, they will be able to solve the open problems which you have told in your talk. And now I take that opportunity for the participants. So if any participant want to ask any query or any doubt, he or she can ask.
Sorry
Anjan, you may ask your question.
for my bad throat. I don't know whether it disturbed my talk.
No, it was
Hello.
fine,
Good.
ma'am.
Hello,
It was
good evening,
fine.
ma'am.
Yes.
Ma'am, my question is, are the path independent, ma'am? The cover which we are choosing, are they independent? I mean, the way I am choosing the cover, it may differ from others, right, ma'am?
I don't understand your question.
Ma'am, the path cover which we are choosing, ma'am, for the graph,
Yes.
it may differ from person to person, no, ma'am? It may
Yes.
differ.
Yes.
Ma'am,
I
then
showed you. Given
Can
it-
we say?
Yes.
Can we say that which one is better one, or is there something like that? That this cover is better or that cover is better?
No, actually, a problem in what respect you want to. For example, I have already defined a psi dominating set, and corresponding to psi dominating set, whenever a finite psi dominating set exists, I can define a psi domination number, which I have not done in this talk because there was no time. My theme was different. So then you can calculate psi domination number, and out of all the psi domination numbers corresponding to different graphidal cover, the one which has the minimum could be considered the better one.
Oh, okay. Thank you, ma'am. I got it.
Also, we have introduced another parameter, graphidal length. So corresponding to each graphidal cover, there is a number that we have defined, and then we have taken the maximum of that number. So that is also there. You can study that also.
Okay, thank you, sir.
Okay.
It depends on the motive. Depends on the motive. But like if you are fixing the routes, so what actually that whenever a truck is passing through interstate or something, so you are having certain checks. So you want to have minimum number of checks. Or if the time is the constraint, then how to route. So graphidal covers can be used in several ways. In communication also. Anybody else, please?
Okay, so next we
Thank you, ma'am.
Next we have the question from Professor Jairam. Sir, you can unmute yourself and ask your question.
Thank you, Purnima. It was a nice talk.
Thank you.
Seeing you after a very, very long time in the late 90s.
Yeah, thank you so much.
With Acharya and in conferences. It was a good talk. My question is, see, you have defined the dominating set and the graphidal covers. What about the other covers such as neighborhood set, then the vertex cover, independent notion, edge independence number? Are they all
Actually,
studied?
as I explained to Professor Jairam, that everything which we have talked in graph can be raised further to graphidally covered graphs.
Correct.
It gives whatever,
Correct.
like you're thinking of vertex cover. So same thing, this cover is, they work differently used there. So
Yeah.
I can now, I can think of psi vertex cover,
Correct.
psi independence. Actually
Correct.
now there are
Has it
there
been
are-
done? My question is, has some work been done in that area?
No, we should jointly do it.
Oh, good, we will. And another thing that I want to remark is, you must have seen the book by Sampath Kumar and other people on semi-graphs.
Yes, yes, very much.
Even that actually happens to be a graphoidal cover in one sense, because there they take for finite graphs all edges of length 1, 2, 3, etc.
Yes, yes, yes,
But extension to infinite semi-graphs is not done actually.
yes.
I think that
Let
would
us-
be another good area to explore together.
Yes, very much, Dr. Jay.
Yeah, it was very nice to see you and hear you. I have mailed you. Let us be in touch.
Yes, yes, very much. Thank you
Thank
so
you, madam.
much.
Thank you.
Hope the participants enjoyed the talk.
Next question we have from Vinci. Vinci, please unmute yourself and ask a question. Vinci.
Okay, thank you, ma'am, for the nice presentation. So I have a doubt. Do you have any survey paper to refer about graphoidal cover of a graph?
I have already given the references, and there you will find everything. If you read one paper of 30 pages in discrete mathematics, you will know everything. Not only this, many, many more things.
Okay, okay, thank you, ma'am.
And there is one creative review also, creative review paper by Professor Arumugam and I think PDHRS sir. So, but that is very old paper, but it contains lot of parameters and related to graphoidal cover. So you can reference that also.
Okay, ma'am, and the one example from the before the first question. Can you?
Okay, let me share this slide. I can share this slide.
Okay.
What is the question, Rajesh?
She wants to refer to some slide, ma'am, first. Some slide of yours. Okay, so which slide?
The one example for side dominating set. The last example.
Side dominating set.
No, before this.
So before
This one?
Before. Yes, this one.
Previous one, previous one.
Yes,
here,
yes.
here no, this the previous one.
There are two images, this one and this one. Which one you want?
Next.
Okay, this.
Okay. Here there is a small doubt. If D is dominated by any
D and A are adjacent. D and A are adjacent in the graph and also in the graphoidally covered graphs. D is psi adjacent to A and C is psi adjacent to B. You see the tangent.
okay.
C is internal vertex of the psi is ACE and D is internal for BDF.
B. Okay.
And therefore AB is psi dominating set.
Okay. Okay, thank you, ma'am.
Okay. So next, any other questions from any other participant? So I think there are no more questions.
Yes. So again, I very much thank to Dr. Purnima Gupta for her nice lecture. And
Thank you.
ma'am, I wish to ask one thing. Is there any work about psi adjacency matrix?
On matrices, so far no.
Okay.
But
Nobody has done.
But if someone is working on the matrices, so it's a very good. I think Dr. Acharya also suggested one time. He said we can think of corresponding to like there we are having matrices. So
Yes,
different size, different matrices can be made.
Because we have defined psi adjacency.
Yes, very much.
That means psi adjacency matrices can be defined.
Yes, very much. Because different size, psi 1, psi 2, psi, and different matrices, and then the way it is being worked, and then we can compare also as we
Yes,
people are working on the energy or spectra and the eigenvalues. Those can be worked on.
So it's a new horizon.
Yes, yes, very much. Thank you.
Okay.
for the
Okay. Thank you
suggestion.
again. Thank you very much, ma'am.
Thank you.
Thank you, ma'am.
So,
Thank you, Dr. Rajesh.
Thank you, ma'am. So Praveen sir, we can go for the next session, next lecture by
okay.
Deepa ma'am.
So should I start?
Yes, Deepa ma'am is here, so we can start.
Okay. So again, welcome to all the participants.
Sorry,
Now it is.
Dr. Praveen, one moment. Dr. Rajesh, is there any question from Professor Sampath Kumar? Because this is being started by him only.
I don't know, ma'am, because he has not raised his hand.
Okay, that's okay. Sorry, Dr. Praveen. Sorry.
No problem at all, ma'am. So yes, welcome again to all of you. Now it is my privilege and honor to introduce respected, dynamic, and renowned graph theorist, Professor Deepa Sinha. Ma'am, she did MSc in mathematics from IIT Kanpur and PhD in applied mathematics from Delhi University under the guidance of respected and eminent mathematician Professor Mukti Acharya ma'am. She has served several institutions, particularly Khalsa Girls Degree College from 1996 to 1999, Delhi College of Engineering from 1999 to 2004, Banasli University from 2004 to 2012, and presently she is professor in the Department of Mathematics, South Asian University, Delhi. She has also served as head of the department in South Asian University from 2016 to 2018. She has more than 120 research papers to her account published in journals of national and international repute with high impact factor. She has guided 14 PhD students and 7 MPhil students. She has organized or coordinated more than 40 conferences, workshops, or training programs. She has delivered several talks as a resource person or invited speaker at different places in India and abroad. She is principal investigator to a project sanctioned by DST SERB under Matrix project. She is member of 5 highly reputed societies of mathematics. It is a great fortune for me to do my PhD research work under the guidance of such a great, respected, and well-known academician, Professor Deepa Sinha ma'am. With these remarks, I invite Professor Deepa Sinha ma'am to deliver a talk on full-friendly index set. Over to Professor Deepa Sinha ma'am.
Ma'am, you are muted right now. You have to unmute yourself first.
Thank you, Dr. Praveen, for your kind words. Thank you. And I again thank the organizer. Yeah? Anything? Rajesh?
No, Praveen sir was thanking you.
Okay. Thank you, Praveen, and everybody for giving me for such a nice words, and also to the organizers for giving me the opportunity to place my work before the audiences. So today, yesterday I gave some idea of the friendly index set. So today I'll just continue that only. Okay. So let me share the screen. I think it's visible to everybody.
Yes, ma'am, we can see.
Yeah. So I'll again start with just to brush up whatever what is the definition so that we can catch up with the later work on the friendly labelings. If G is a graph having the vertex at V and the S at E, and F is the labeling from the vertex at 2 modulo 2 integers, then it induces the edge labeling F star on the S set EG to Z2, which is defined as F star of any edge XY will be equal to the absolute difference of Fx minus Fy, where X and Y are the members from Z2, and XY is any edge in the graph G. Now, for I belonging to Z2, VFI will denote all those vertices of the graph G receiving the value. Z2 is containing only 0 and 1. So VFI will be taking the value 0 and 1. So VF1 will be all those vertices. VF1 is the notation for all those vertices receiving the receiving the value I. That is, it will be either 1. If it is VF0, then number of vertices receiving the value 0 on the vertex, and number of vertex receiving 1 will be denoted by VF1. And as told you, friendly index is the generalization of the cordial, friendly labeling is the generalization of the cordial labeling. uh, so here we don't have any such condition on the edges, but then we do calculate the values on the edges, like how many. So edge will, because of this formula, F star xy is equal to difference, absolute difference of Fx minus Fy. So this edge will also receive the value 0 and 1. So EFI will denote the number of edges receiving the value I. That means EF1 will denote the number of edges receiving the value 1, and EF0 will denote the number of edges receiving the value 0. And labeling F of a graph G is called friendly when the number of vertices labeled 1 and the number of vertices labeled 0, if I take its absolute difference, it is either equal to 0 or equal to 1. Okay, so it should be less than equal to 1. So friendly labeling can be done in many ways. Okay, so if the friendly labeling can be done in many ways, it is interesting to calculate the friendly index, full friendly index and all that. So I'll just come to those definition. A vertex V is called K vertex if the vertex V, if the function if the vertex V receives the value K, then we call it as a K vertex. Sometimes that is K will be what? K will be 0 or 1. So vertex V will be called as a 0 vertex if it receives the value 0, and it will be called as a 1 vertex if it receives the value 1. And similarly, the case is with the edge E, because E will also take the value 0 and 1 according to this formula by the function F star, that it is the absolute difference between Fx and Fy. So it will also take the value 0 or 1. So then the edge will be also called either as 0 edge or 1 edge, as the case may be. And then friendly index IF notation is given by IFG. This will be equal to number of edges receiving 1 minus the number of edges receiving 0. This will be called as the friendly index of the friendly labeling F. So with the different labeling, this may differ, because with one friendly labeling, this may have some value. With another friendly labeling, this may have different value. Because friendly labeling is what? Half of the vertices you are labeling 1, and half of the vertices you are labeling 0. So it can be done in many ways, but only when it can be when the number of vertices is even or the order is even, then half you can divide it into half and half, and then you, wherever you want, whichever vertices, there can be so many permutation of labeling 1 and 0. Okay, so now with different labeling you will get different friendly index. That's what we'll come to that example again, so that. And the friend fxg, that is the friendly labeling f, such that the friendly index is equal to x. Suppose if this friendly index comes out to be x, then that all those labeling f, these are friendly labeling, all those friendly labeling for which friendly index is getting the value x, that will be called as a fxg. That will be denoted by, this set will be denoted by capital F. This x is the number that you are getting of the graph G. And fg, if I just denote without the suffix x, fg will denote the set of all friendly labelings of the graph G. Then we have the following definition: the maximum friendly index will be denoted by phi g. Okay, so because we are having different friendly index, so maximum will be denoted by capital phi g, and that is, it can be maximum of ifg, f belonging to the friendly labeling, and the corresponding labeling f is called maximum friendly labeling of g. What happened? Okay. The minimum friendly labeling is denoted by phi dash g, and this will be the minimum of the friendly index on the friendly labeling f on the graph G. And the corresponding labeling is called the minimum friendly labeling of G. And what is maximum modulus? Because this may take the negative value also, negative or positive, because what you are doing, you are subtracting ef1 minus ef0. Okay, see, this is ifg is ef1 minus ef0. If one number of edge labeled 1 is less than the number of edge labeled 0, then this may take the negative value. Okay, so sometimes enumerating all the negative and positive edge indices is useful, and sometimes only the positive indices, enumerating only positive indices will be of use in the model that one is working on. So this will be minimum IFG will be, and the corresponding labeling F will be called as the minimum friendly labeling of G, and the maximum modulus friendly index is denoted by psi G, which is defined as maximum of, this is modulo value. So it will always have the positive value for any F, friendly labeling F belonging to the friendly labeling set of G, and the corresponding labeling is called maximum modulus friendly labeling of G. And similarly, one can define for the minimum modulus friendly index, that is, notation is psi dash G. The friendly index set of the graph G denoted by Fig is defined by the collection of all the, see, there can be, as I'm continuously telling, that there can be many friendly index. So many ways you can label 0 and 1. There can be so many permutation. Okay, so the cardinality of IFG such that, so it will, this is a set where f is not the cardinal, this is the absolute value of ifg. So all those that will be the set of all the absolute value of the index depending on different friendly labeling will be contained in a set, and that set will be denoted as fig, which is called friendly index set. And full friendly index of the graph G is denoted by ffig, which is, you are not taking the modulo value, you are considering both the negative and positive value. Okay, because once it may take the negative value also, but here you have ignored the negative value, you have considered the absolute value. Here you may take the negative value also. So the set of all negative positive values depending on different labeling, that will be called as a full friendly index set of the graph G. And then a subset, any subset x of the integer set z is said to be fi representable, that is full friendly, that is friendly index representable. If you can for the subset x, you can find a graph such that the full friendly index of the graph G is that set x, subset x of the z. Okay, so as we say that the graph is, see, this is same as we say that the given set of number is graphical only when it satisfies certain condition, that the sum is even and all that. So that is same is this, that you are given any subset of the integers, can you say that this is friend, if those subset, those elements of the set X can form the friendly index set of any graph, friendly index of any graph G, then it will be called as a friendly index. This set X will be called as a friendly index representable. And if it represents total negative, if you take both negative and positive value, because Z is a integer set, so if X is then it may be FFI, the graph may be FFI, the set X may be FFI representable if FFIG is equal to X. Now if we consider some arbitrary graph. Okay, so now see the friendly labeling, as I told you, there are how many vertices? 1 2 3 4 5. So 5 vertices. So for friendly labeling you have to label half of the vertices 0 and half of the vertices 1. Okay, so once it, because the number of vertices are odd, so you cannot label half, so you can either label half but one vertices as 0 and the rest of them as 1, or half but one vertices as 1 and the rest as 0. So as you see here, in this case only two vertices are labeled 1 and three are labeled 0. So the edge will be, this will be receiving 0, this will be receiving, this edge will be receiving 1, this edge will be receiving 0, by because what is the edge label? Edge label is you have to subtract the end, the labelings on the vertices. So this will be 1, this will be 0, this will be 0, and here also it will be 1. So there will be, how many ones are there? 1 2 and 1 2 and then 3 4. So 1 2 3 and 4. So 4, and how many zeros are there? This is 0, this is 0, this is 0. So 4 ones are there and 3 zeros are there. So IFG will be equal to 4 minus 3, which will be equal to 1. Similarly, if we label, like in this case, when you have labeled this as 1 and this as 1, okay, then you may get IFG is equal to 3, because again if you work out, so this will be 1, this will be 0, the edge labeling on this will be 1, this will be 0, this will be 1 1, and then 1, and then 0, and then 1. So in this case, the number of labelings, edge labeling as 1 is 1, this is 1 2 1 2 3 4, and then number of labeling 0 is uh, 1 2, I think I'm making some mistake. So it is 1 2 3 4, and then 0 labeling is 1 2. So it should be equal to 2. I think there is some mistake. Okay, similarly you can see that in this, and in with some labeling you can have IFG is equal to -1 also. Okay, so now if -1, when will you get? When the number of one labeled vertices, when the number of zero labeled edges are more than the number of one labeled vertices, one label edges. Okay, then you will get negative this thing. If F is a mapping from vertex set of vertex set to Z2 and it is a friendly labeling, so its inverse labeling is also friendly. Is inverse labeling VG from G, defined as G from vertex set of G to Z2, defined as GV is equal to 1 minus FV. See, F is a mapping from vertex set to Z2 and G is a mapping again from vertex set to Z2. G mapping will be called as inverse if you reverse. Like if it was like in this example, if it was 0, it has been reversed to 1 minus 0, that is 1. If it is 0, then it is 1 minus 0. So it will be, when it is 0 here, it has to be 1, and if it is 1, it has to be 0 over here. Okay, so in this case, we see that if we take the inverse labeling, the it does not affect the friendly index, because you just see here the number of zero labeled edges are 1, 2, 3, and 4. Okay, and then the number of one labeled edges are 1, 2. So 4 minus so then 2 minus 4 will make it minus 2, and similarly here, because just you are reversing, so here it does not affect. Okay, so that is why it is again very interesting to note that for the inverse labeling, the friendly index set remains the same. Friendly labeling can be viewed as a generalization of the cordial labeling, as we have already talked yesterday. As I already told you yesterday, friendly labeling is the generalization of the cordial labeling, because in the cordial labeling, you know that the difference, absolute difference between the one labeled edges and the zero labeled edges must also be less than equal to 1, which is not the case with the friendly labeling. For a graph G, if any of the friendly index value minus 1, 0, 1 exist, okay, then the graph is a cordial graph. So this has been found that if for any friendly index values minus 1, 0, 1 exists, then the graph will be a cordial. Then the friendly level graph will also become cordial graph. That is that is the number of edges labeled 1, absolute difference of the number of the edges labeled 1 and the 0 will be less than equal to 1. For example, in literature, it is shown as a corollary that if you take the union of the cycle on m vertices and n vertices, it will be cordial if and only if m plus n will be equal to m plus n will be either equal to 0 mod 4 or 1 mod 4 or 3 mod 4. See, mostly I have not mentioned over here, but mostly it has the work on friendly labeling is done by Shu, Lee, NG, and all these people have worked on the friendly labeling, and still many papers are coming up. And after this, Shu and Lee and all that, I think me with my student have worked on the friendly labeling. However, Karine and Edward prove that graph which admits cordial labeling is NP complete. Therefore, it is when once it is NP complete, it is to make a generalization is also very difficult. Only for the particular class you can find out the friendly index. Then it has it is also used in minimum bisection problem. Clearly, solving the minimum bisection problem is equivalent to finding friendly labeling set with minimum EF1 value. Okay, where F is ranging over the set Fg of all friendly labelings of the graph G. So F is it can there can be so many friendly labeling, and you have to find out the minimum of the EF1, where you can get the minimum EF1 value. The problem can also be viewed as finding, as I have told you, the notation phi dash G, because phi dash G was the minimum friendly index, okay, and F of phi dash G, that is the set of the friendly labeling on which you get the minimum of the friendly index. Therefore, one looks forward to solving the problem for specific classes of graph that admit a good solution, in the sense that there does not exist a polynomial time algorithm to solve minimum bisection problem, and that is what has been our approach also. And then balance sign graph. So because in the partition is in balance sign graph also, the vertex set can be partitioned into two subsets, okay, such that the negative edges lies across. So here also one can see for the balance of the society also such modeling can be taken up. Then max cut problem. the well-known Max-Cut problem of classical graph partitioning problem, which asks for the partition of the vertex set v1 and v2 of the vertex set G, where G is a weighted graph that maximizes the total weight of the edges with one n in each vi. This problem is again NP hard, and the unweighted version of Max-Cut problem is often called maximum bipartite subgroup. So all these problems, so there has been so many uses when you so first of all, actually we need to learn the how to do it, and then we can, if we know few of the problems already been tackled using friendly labeling, then we can think of some more problem which can be done by using Max-Cut problem. So it can be done for judiciously partitioning problems. It can be used for modeling judiciously partitioning problem. Then okay, so friendly labeling, we certain preliminary results are there which can be handy or useful while proving the further results. So uh, friendly labeling will always be denoted by F. Let F be any vertex labeling of the graph G such that, very interesting, let F be any vertex labeling of the graph G such that degree of V is even whenever its label on the vertex is 1. Whenever the label of the vertex is 1, that, because it is label of the vertex will be given to the graph by this function value. Okay, and coincidentally, if it happens that the vertices receiving 1, the degree of that vertex is also even, then ef1 will also be even. That is, the number of edges labeled 1 will always be even. Okay, so this can be verified by handshake lemma. So we can, I think we, because EF1 is actually, what is EF1? EF1 is actually the sum of the edges receiving the value 1. Okay, so that is this, and then this is, if I break it, this will be, because degree of V is even, so this will be summation V belonging to V, degree of V into FV modulo 2 addition, and this will lead to that EF1 will always be equal to even. And then let, if G, so again a generalization, if G is an Eulerian graph, we know that every vertex is of even degree, then EF1 is even for any vertex labeling of F. Any vertex labeling means any friendly vertex labeling. F is always friendly labeling. Okay, so that means half or half but one vertices are labeled 0, or half or half but one vertices are labeled 1. Let G be a PQ graph, then full friendly index set will always be a subset of 2i minus q, where I is varying from 0 to q. Q is the number of edges. Full friendly index set, it has been also found that that full friendly index set for any graph G will lie between 2i minus q, where I is varying from 0 to q. Why? Because if F is a friendly labeling, then EF1, if EF1 is equal to I, suppose it is some sub I, then what is EF0? EF0 will be rest of the edges minus I. Okay, because there are only two values edges are receiving, either 0 or 1. Hence, the friendly index of the graph G will be equal to 2I minus Q. So that will depend on, therefore the full friendly index set will always be a subset of this set, 2I minus Q, where I is varying from 0 to Q. Again, if G is connected graph of order greater than 1, then full friendly index set will be always, full friendly index set of the graph G will be a subset of 2I minus Q, where I is varying from 1 to Q. Because since F is friendly labeling, since G is connected of order greater than 1, there exist adjacent vertices, that is, there will exist a path between every vertex, so every pair of vertices. Okay, so so some of them may be adjacent also, xy suppose, such that if the labeling on x is equal to 1, and if the labeling of on y is equal to 0, then ef1 will be greater than equal to 1. And then we have another lemma that for any graph with q edges, the friendly index set Fig will always be a subset of 0 to 4 up to q if q is even. That is, see these are the results all from seen by Xiu Li and all those people. If q is even, that is, if the number of edges is even, then friendly index will be lying within this set. Even all will this 0 to 4q. And if friendly index of the graph G will be 1 3q if q is odd. So these are very interesting results that one can see. And if one has any problem, basically I see that if one has a cryptographic problem, encryption decryption problem, one can easily use all these techniques and then have a better encrypted or decrypted sequence, so that encrypted sequence, so that nobody is able to decrypt it. Let f be, until and unless they know about friendly labeling, okay, let f be a labeling of a graph G that contains a cycle C as a subgraph. F is a friendly labeling and contains a cycle C as a subgraph. Then C contains one, and if C contains one edge, that is, if due to friendly labeling, if any one of the edge is, if some of the edge or any at least one of the edge is receiving one, then the number of one edges in C is a positive even number. This can also be seen due to all this corollary above. So for n greater than equal to 3, the full friendly index set of the graph of the cycle Cn, if the graph is only cycle with n number of vertices, then this will be uh, the subset of this will be a subset of 4j minus n, where j is varying from 1 to n by 2. Because f is a friendly labeling, so because of the lemma above, we can see that and ef1 will be equal to 2j. That is the number of cycle we said na, if it has a cycle, if any of the edge is labeled 1, then it has the even number of edges which is labeled 1. So here also the number of, because it is only a cycle graph, so it trivially follows here that ef1 will be equal to some even number, say 2j, where 2j will be varying from 2 to n. And index set, friendly index set cn of cn will be equal to 4j minus n, where j will be varying from 1 to n by 2. If G is a two connected graph, that is, at least two vertices you need to take out so that the graph becomes disconnected, of order greater than 1, then full friendly index set of the graph G is a subset of 2i minus q. It will be a subset of 2i minus q, where I will be varying from 2 to q. So I'll be sharing these slides to the organizer, so that they may send it to who all are asking, and then you may go through the proof. Okay. Then if G is 2 connected, now when again you reduce the condition, that is, if it is 2 connected, and that too it is a bipartite PQ graph, okay, with number of vertices greater than equal to 2, and EF0, that is the number of edges labeled 0, is not equal to 1. Okay, so then q minus 2 will belong to, then q minus 2 will not belong to the full friendly index set of the graph G. Because if f is a friendly labeling, then any cycle C in G must be a even cycle. Okay, because since the number of one edges in C is even, so the number of 0 edges in C will also be even, and therefore EF0 cannot be equal to 1. So if A and B are two friendly index set, and let S and T be two positive integer, then we define this SA plus TB is equal to SA plus TB, where A belonging to A and B belonging to B. General addition in algebraic addition. Okay. So this addition is also taken up for full friendly index set. So let H be again another important lemma. Let H be a PHQ. Let H be a PQ graph, because it is denoted, because there are two sub graphs in consideration. So what we denote? So we denote PH and QH for H, and then PK and QK for K. Then if I multiply pk, number of vertices on k, on this k graph, and full friendly index set of the h, plus number of vertices on the h graph into full friendly index of set of the k, then this becomes a subset of, very elegant result, this becomes a subset of the full friendly index set of h cross k. That is the this is a Cartesian product of H and K. Okay, so these are the very crucial findings which may lead to many applications. Let H be a PQ graph, because it is for mention for H, so PHQH with friendly labeling H, and K be a PKQK graph. If so, here we are not saying anything for PKQ. For H graph we are saying that there exists a friendly labeling H. Then if if number of vertices in the graph H is even, then the friendly index set of the graph H into pk minus qk is the number of edges in the another graph, into ph will also be a subset of full friendly index set of the Cartesian product of H and K. Let m be greater than equal to 1 and m be greater than equal to 1 and less than equal to n. Then for a complete graph KMN, complete bipartite graph KMN, we have friendly index set of the KMN is equal to m minus 2i whole square, where I is varying from 0 to m by 2 if m plus n is even, and it is divided into this. Condition is divided into 2 when m plus n is even, the bipartites. Okay, so m plus n is even or m plus n is odd, we have this condition. And so from this one can generalize that, one can find out for the star that for when full friendly index set for when m is equal to 1 and n, this will be equal to 0 2 if n is even and 1 if n is odd. You can calculate from this. The friendly index set of a cycle is given as follows. If the cycle is of even length, then it will be 0 4 8 2 n if n is even, and if it is odd, then it will be, see, it is the multiple of 4, and here it is 2 6 10 2n if n is odd, and if n is odd, and then see c2n, where it is again, either you can write it in 4 into n or just like this, because if we are writing c to n, n may be even or odd. If n is even, then we have this. If n is odd, then we have this. Or and uh, if n is if 2n plus 1 is 2n plus 1, everybody knows it will be odd. Okay, then this will be 1 3 5 2n. These are the friendly indices, 1 3 5, all the odd integers. Similarly, one can see that for any integer n1 and n2 satisfying n1 and n2 greater than equal to 3, if we define s as equal to 0, 4, 8 up to n1 plus n2, if n1 plus n2 is equal to 0 mod 4 is equal to 2, 6, this set 2, 6, 10 up to n1 plus n2, if n1 plus n2 is equal to 2 mod 4 and is equal to 1 mod 4. Then if either n1 plus n2 is less than equal to 1, cardinality absolute value of this, or both n1 and n2 are even, then friendly index set of c n1 n2 will be equal to s. Otherwise friendly index set of c n1 n2 will be equal to s minus n1 plus n2. So this is what is c n1 n2. These are two regular graph, one two regular graph. So it can be because it is showing two in this values n1 and n2, so it is disconnected two regular graph. That is, there are two cycles, one with the number of vertices n1 and another with the number of vertices n2. Suppose G is equal to C, N1, N2, Nk, and let N be the sum of the these are the actually the number of vertices on the two regular graphs, and L be the on each in each component of the two regular graph, and L be the total number of odd cycles among these k cycles. There are k cycles. So if we let S is equal to this when n is even, and this all this we need to, this is not an easy task, one has to work hard to get all these numbers. And then we see that the full friendly index set of C, N1, N2, Nk, where there are k components of a cycle, first component with n1 vertices, second component with n2 and kth component with nk vertices, then full friendly index set will be equal to S, where S is given like this when n is even and when n is odd. This is the condition given on the total number of vertices. And okay, then full friendly index set of a complete graph Kn. The full friendly index set of a complete graph Kn is n by 2. It has only one value, n by 2 when n is even, and is equal to n minus 1 by 2 when n is odd. Why? Because see, when n is even, half of the vertices friendly labeling, you are by the definition of friendly labeling, half of the vertices you are labeling 1 and half of the vertices you are labeling 0. I'm just talking about the first case. Okay, so let V0 denote the number of vertices receiving the level 0, and V1 denote the number of vertices receiving the level 1. When n is even, then the cardinality of the vertices receiving 0 will be n by 2, because n is even, half of them will be giving taking 0 value, and cardinality of the vertices receiving 1 will be n by 2. So every edge, very important, see, every edge within V0 or V1 is zero edge, because in complete graph all the vertices are connected to every other vertex. Okay, all the vertices are adjacent to each other. So if you take the subgraph induced by the 0 level vertices, or you take the subgraph induced by the 1 level vertices, then every edge within that V0 will be, or in V1 will be zero edge, because if within 2 end vertices are 0, edge will also receive 0. 2 end vertices are 1 in V1, all the 2 end vertices and the end vertices are 1, so again the labeling will be on the edge, it will induce the 0 labeling on the edge. So the number of 0 edges, because since it being a complete graph, it will be equal to n by 2 into n by 2 minus 1, and every edge from V0 to V1 will be one edge. Now if there is an edge from 0 level vertex to 1 level vertex, then the edge it will induce one level on the edge, and so the number of one edges will be equal to n by 2 into n by 2. Okay, so therefore the full friendly index set will be equal to, of the Kn will be equal to n by 2, because what you are doing, full friendly index set, you will be subtracting one labeled vertices minus the number of vertices receiving, edges receiving 1 minus number of edges receiving 0, and it will give you this set. And similarly one can see that, so there, when n is odd, I'm just doing few of the examples elaborately, so that when these things, when I only speak, then also you may just it may just click to you that maybe something of that sort is happening there also. So clearly cardinality of V0, Either the cardinality of V0, because n is odd, it will be n minus 1 by 2, and cardinality of V1 will be n plus 1 by 2, or the reverse. V0 will be n plus 1 by 2, and V1, cardinality of V1 will be n minus 1 by 2. So if cardinality of V0 is equal to n minus 1 by 2 and V1 is equal to n plus 1 by 2, if this is the case we are restricting to, then every edge within V0 and V1 will be 0 edge as seen. So number of 0 edge will be this n minus 1 by 2 into n minus 1 by 2, and from every edge from V0 to V1 there will be one edge. So the number of one edges will be this, and therefore full friendly index set will be equal to n plus 1 by 2 into n minus 1 by 2 minus n minus 1 by 2 into n minus 1 by 2, which reduces to n minus 1 by 2. Similarly, one can go for the other case. Okay, so this is for any natural number a greater than equal to 4, the set A is full friendly indexable. Why? That means you are able to find a graph for which A becomes the friendly index. Friendly index. So for any A, why? Because if you put n is equal to 2a or n is equal to 2a plus 1, see in this graph, for if n is equal to 2a, if the number of vertices is equal to 2a, then this will reduce to 2a by 2a, and if the number of vertices is equal to 2a plus 1 for the second case, then also it will give the friendly index set A. So that means A will always form. This is any number from the, so this is subset of integers. So this is full friendly representative. So whenever you come to see, so what we are doing actually, getting hold of this result. First of all, you find out this result. Once you get this result, you can find out from seeing this that you can find out the integer which can work for which can work as a friendly index. Okay, so that is what is as it is being done over here, and it is done for other graphs also. Note that the friendly index value remains very elegant. No, friendly index value remains invariant with change in friendly labeling. So friendly index value will not change with change in friendly labeling, which include there can be a case that it's not always so, but in some cases the friendly index value will remain invariant however you take the friendly labeling. As in the previous example, I was taking friendly labeling, sometime here one, sometimes some other vertex labeled one. My only intention was that half of the vertices labeled 1 must be labeled 1 and half of the vertices must be labeled 0. In case if it is even and odd, then half but 1. Then the graph G is said to be uniformly friendly graph, because for any F you are getting the same friendly index. So this such a type will be called as a uniformly friendly graph if the value of friendly index if the value of friendly index, that is IFG, is independent of the choice of friendly labeling. Okay, so then the natural question arises that characterize all the uniformly friendly label graphs. Okay, then full friendly index set of a cycle. The full friendly index set of a cycle Cn is given by this FEFCN will be equal to 4i minus n. I think this is meant for the edge. I must skip this. This we have already covered earlier. Okay, so let us see full friendly index set of a wheel. Now Wn is denoting means n minus 1 vertices are on the circumference and one vertex is on in the with one vertex in the center. So let F be a friendly labeling of wheel W2N, where N is greater than equal to 2. Then the minimum and maximum value of EF1 are N plus 2 and 3N minus 2 respectively. This you can work it out, but we have worked it out, and then let F be a friendly labeling of the graph W2N plus 1. Okay, this is the wheel on odd number of vertices. Of course, N is greater than equal to 2. Then the minimum and maximum value of EF1 are N plus 2 and 3N respectively. Okay, and for the wheel Wn, N greater than equal to 2, there are certain integers N plus 3, N plus 5, 3N minus 3, there for which there exists no friendly labeling such that EF1 is equal to C. So these values can never be taken by as a friendly index. Okay. So again, there is a proof for this. For N greater than equal to 2, the full friendly index of a wheel Wn is 2i minus 4, set of 2i minus 4n plus 2, where I is varying from n plus 2, n plus 4 up to 3n minus 2. And for the odd number of vertices, it is 2i minus 4n. For the even, it is 2i minus 4n plus 2. And for odd, it is 2i minus 4n. I is equal to n plus 2, n plus 3, and 3n. So seeing this, you can find out the indexable, these 2a, 2a minus 4, 6 minus 2a, and 2a, 2a minus 4, 4 minus 2a are all friendly, full friendly index representative. In a wheel, however you take, EF1 will be equal to 3n minus 2, and EF1 maximum value will be 3n minus 2, and minimum value will be of which on different labeling you get well, you can label differently, na? So how you decide your labeling, depending on that you may get minimum and maximum value. So minimum value in every case will be equal to 3n minus 2, and maximum value, minimum value in every case will be n plus 2, and the maximum value will be 3n minus 2. So this is the wheel. These are different examples. Okay. So now these are, if I put v1, v2, vn minus 1, vn plus 1, vn plus 2, v2n as the vertices on the circumference, and v as the vertex on the center, then v can be labeled 0 and v can be labeled 1. Okay. In both the cases, you get minimum value 3n minus 2, minimum value n plus 2, and the maximum value 3n minus 2. So again, friendly labeling. See, half of the vertices are labeled because you are increasing. You are putting 0, so number of zeros are increased by 1. Okay. So here also the same thing. So here it is labeled in a different manner. Here alternately 0 and 1, with 0 as a center, and still the maximum value of EF1 is 3n plus 2, and minimum value of EF1 is n plus 2. Similarly, one can find the full friendly index set of a fan. So fan will be like, there is one vertex, it will be like a star, star plus k1n plus path pn. K1, so I think I have the graph. This is a star, this is a fan graph, So this is like you have these but edges and then they are joined like this. Let f be friendly labeling of the graph fm m greater than equal to 2, then the minimum maximum value of ef1 in case of fan fm are m by 2, upper ceiling m by 2 plus 1 and upper ceiling m by 2 plus m minus 1 respectively. And then the full friendly index set of FAM, which can be calculated, is 2i minus 2m plus 1, where upper ceiling n by 2 plus 1 is I is greater than equal to upper ceiling m by 2 plus 1 and less than equal to m by 2 upper ceiling plus m minus 1. For any natural number a greater than equal to 2, the sets 2a minus 1, 2a minus 3, 2a plus 1, 2a minus 1 minus 2a plus 5 are full friendly index representable. See, again, this has been calculated from here. In this case, to find when m is fm when m is even, so in that case, maximum ef1 will be equal to upper ceiling m by 2 plus m minus 1 and minimum will be upper ceiling m by 2 plus 1. Then V can be labeled as 0 and 1 and you can say verify for every case.
Sorry to interrupt, ma'am.
Yeah.
We have some more time. We have some only 5-10 minutes.
Okay. I'll just complete in time. I was just seeing if I can. Okay. Animation is no problem. Whole friendly index set of the fan F2M means it is like this. Okay. Fan 2M is defined as a join of K2 and path PM, that is K2 plus PM. So it is like this, where we are labeling two vertices V1, V2 and the all those edges lying in between will be U1, U2, U3 up to UM. Okay. Then the fan F2M is defined as F2M if it is defined as a join of K2 and PM. So it will be like this. And so actually we will be using this as a lemma to prove the result for the bigger this thing. Like for this subgraph, if we are able to predict something, then we can predict for the whole graph. Okay. So let F be friendly labeling of F2M, M greater than equal to 4 and A, this is the figure A, be the subgraph of F2M such that the labeling F dash is the restriction of F on A. The labeling F dash can be extended to a labeling G dash of B such that the labeling G defined on F2 M plus 2 as, now we according to this we are labeling G as G of B is equal to FB when E belong to F2M. Okay, this is F2M and G dash B is equal to when E does not belong to F2M. This will be friendly, then this labeling becomes friendly because first of all we have to label friendly also, and the number due to this label friendly labeling G, the number of edges labeled 1 will be equal to number of edges labeled 1 due to F plus 2. Which we can see it over here. So this is the center one, pink one was a F and then the rest are coming up. Okay. For the fan F2M, there exists friendly labelings F and G so that EF1 is equal to 2M minus 1 and EG1 is equal to 2M. That is the number due to the friendly labeling G, the number of edges labeled 1 will be equal to 2M. Let F be friendly labeling on the graph F2M, M greater than equal to 2, then minimum and maximum value of EF1 are M plus 1 and 2M respectively, and so forth. So there are so many results, and for F2M, you can have this general result. So I'll just come to, okay, let me, if I have very less time, let me just go back to, there are other, this was due to vertices, okay, and there can be edge labeling also. So I'll just go to that so that I can, just two more slides and then I will stop. Okay. So yeah. So, as we see for the vertex friendly labeling, there where we were inducing the edge, we were inducing the labeling on the edges. यहाँ पे there are edge friendly. We can also define edge friendly labeling where we can induce the labeling on the vertices. Okay, and edge. So this, in once we are putting friendly over here, that means edge are labeled 0 and 1, so that half of the edges are labeled 0 and half of the edges are labeled 1. And how the labels are induced on the vertices, that is this is by you take the sum of all the edges incident on the vertices. I'm not able to see that. You take the sum of all the edges incident on the vertices, modulo 2 sum, and whatever is the value, that becomes the label on the vertex. Okay. So with the pertaining to that, we can talk about edge balance, strongly balanced graph, edge balance index, and so forth. And then with the usual motivation, the edge there, the edge friendly index, edge friendly, full edge friendly index set has been worked out for the edge friendly labeling also. That is what this is the labeling. The vertex is labeled vertex. The induced label on the vertex is FV is equal to summation of FUV modulo 2, where UV belongs to the S set. Okay. And then definition is likewise for the index. So one can go through this, and then okay, then one can see if the graph, if there is a region, we can also talk about region friendly. So edge friendly, region friendly. So region will, we can talk in the planar graph. When the graph is planar and R is a set of regions, V dash be the set of cut vertices in G, VR is a set of vertices in region R, and if BV is the number of connected components in the graph G minus V, then you can have then vertex labeling from vertex V be the function f from V to Z2 will induce a region labeling f star R from region R to Z2, which is defined as this. See, so where from the vertex friendly labeling, you are inducing the label on the regions. See, this will be equal to summation FV modulo 2 when R is a region bounded by a cycle, and when R is not bounded by a cycle. Okay, that means there will lie there will lie some connected components. There will be a cut vertex. In that case, this will be the formula. And this formula is being defined in accordance with the degree sum formula. Okay, so and then similarly, because edge concept is there, so yeah, all these indices can be worked out: region index of friendly labeling, region full region index of the friendly labeling, and all that. And then with respect to edge also, if G is equal to V plane graph and E dash denotes the set of pendant edges and ridges, and R the set of all regions in the graph G, and ER be the set of all the edges, so that E is the edges in the region R, then the edge labeling, because if we are making edge friendly labeling on the edges, then see this part is telling that if we are the first part was that if first of all we are considering the planar graph, and if the vertices are label friendly, how to induce the label into a region, And if the edges are label friendly, then how to induce the label into a region, and then work for the label friendly index, work for the region index, region friendly index due to vertices, region friendly index due to edges, then region full friendly index due to vertices, region full friendly index due to edges. Okay. So, and then when can it be representable? Region, index, edge, full friendly, labeling label representable, full region index, edge friendly, label representable. So all this, the enormous work has been done, and still people are working on this. So I think I stop here. If any questions are there, then one can ask.
Yes.
So I think first question is from Professor Jairam Srirangan. Professor Jairam, please unmute yourself and ask a question.
Sorry, it was the hand raised on earlier occasion.
Acha. Good.
Hello?
It was in your earlier, na, this thing.
Yeah, sorry, I'm sorry. It was a good talk, madam. Congratulations.
Thank you, thank you.
Okay. Any other questions from the participants? Please raise your hand. We will take the question one by one. Okay, ma'am. So I think there are no more questions.
So, on behalf of organizing committee and my personal behalf, I would like to thank Professor Deepa Sinha to deliver such a informative and sparking talk, and I'm very sure all the participants will be benefited with this talk. And in this talk, ma'am had talked about a lot of labeling, and which are very important: friendly, full friendly, and their versions, text, age, region, and many problems she has talked about in her talk. So again, I very much thank to Professor Deepa Sinha ma'am for a sparking and informative lecture. Thank you, ma'am.
Hello, Deepa.
Ma'am, you are muted.
Okay. She has unmuted. No problem.
No, Deepa ma'am is muted.
Deepa ma'am, you are muted right now. You have to unmute yourself to speak.
पता नहीं कैसे unmute हो गया. Okay.
Hello, Deepa.
Thank you, Praveen. Thank you. Hello, ma'am. Hello.
Yeah, though
Hello, ma'am.
I just want to ask, hello. You are taking in this one friendly labeling 0 and 1, okay?
Yeah.
Suppose you take -1 and 1, okay, plus and minus.
We can take what -1 and 1.
Okay, let us not get -1 and 1. I just say plus and minus.
Yeah, we can. That is why it is after every definition it has been compared to balance, na, because it has been compared to -1 and 1.
Okay.
Yeah.
That means then question arises let me say it balanced friendly.
Yeah. You can say.
It's a balanced friendly, be friendly.
Be
Okay.
friendly.
Be friendly.
If you are friendly, you are balanced.
Yeah, that is there.
Similar to the title that productive cordial graphs, right, ma'am?
No, I took a long back. I have taken B cordial labeling. That is basically with the plus and minus. B is coming for balanced, but since the cordial we have two equations. There you will able to get this one, and similarly we talk it B cordial friendly. But every balanced graph need not be friendly.
No, about productive cordial graphs, productive, your title.
Product cordial.
So
Product cordial में actually cordial में they need to see two condition on the labeling on the vertices as well as labeling on the edges.
Yes, yes.
यहाँ पे we need only one condition. Only on the मतलब the thrust is whichever you are working on. If you are working on vertices, the thrust will be only on the vertices to be friendly labeled. If you are working on edges, then the thrust will be only on edges to be labeled friendly. That's all.
If the thrust is on vertices only, okay, that is become, let me call it a B friendly. But my question is, with the balanced graph will be B friendly, need not be.
Need not be. It is not always.
Need not be. The question is, what are those friendly graphs which are B balanced?
जिसमें ना number of edges even है something like that, there are certain results no I have quoted there.
Okay, okay.
We have already worked it out, all those. So under special conditions they become balanced, not always.
That's what. Under special conditions they become balanced. Okay. Okay, then thank you.
Thank you, ma'am. Thank you for your blessings.
there is one more question, I think, ma'am.
Santana
Raju wants to ask a question.
Raju.
Actually, lecture was very good, ma'am. I don't want to ask a question from you. I want to talk Mr. Rajesh Singh, sir.
Okay. So let me go